Good morning or good afternoon. My name is Dimitri Pesha. I'm a Director Power System Transformation at Agora Energiewende, and I want to welcome all of you to today's webinar, Rethinking Grid Stability in Southeast Asia, Learning from the Iberian Blackout. As you know, 3 months ago, actually on the 28th of April, a major power outage struck the Iberian Peninsula, affecting Portugal, Spain, Andorra, and also part of the southwest of France. This blackout lasted for about 10 hours in most areas. It was widely discussed across media outlets, within the expert communities, but also among policymakers and regulators, widely discussed in Europe where it happened, but also all around the world. And it brought actually a renewed attention to a critical aspect of power system, which is power system security and stability, highlighting the urgent need to adapt the way we operate our grids in the context of growing share of renewables. This event intensified the debate on how to maintain grid stability in those systems where more and more inverter-based resources are coming in, so such as wind power, solar power, and battery. With the webinar today, we provide an opportunity to reflect on the cause of this blackout, but we want to go beyond the blackout itself. We want to focus on identifying key lessons and best practices for operating power systems with very high share of renewables. This is indeed a reality which is already present in many regions around the world. So those insights are important. They can inform grid operators all around the world on how to accelerate the transition to renewable-based system in a secure and effective manner. And in the webinar today, we will look at specifically at Southeast Asia, exploring how the region can enhance power system stability while scaling up wind and solar power. So this session is really designed to spark regional dialogue and support forward-looking planning for secure, clean power system across the region. The webinar is part of the CASE project, which is a clean, affordable, secure energy for Southeast Asia. This CASE project brings together several international partners, including Agora, GIZ, and New Climate Institute, and also several partners from the Southeast Asian region, including the Institute for Essential Service Reform, ISR, the Institute for Climate and Sustainable City, ICSC, and the Energy Research Institute of Chulalongkorn University in Thailand. The project is funded by the International Climate Initiative of the German government. So I'm very excited today to start with actually a framing input, which will be provided by my colleague Arne van Stiphout. Arne is actually our expert on grid at Agora Energiewende. He's project manager on grid modernization and other power system transformation with a specific focus on the Southeast Asian region. And after the presentation of Arne, which will last about 30 minutes, we will have a discussion with key experts from the region that I will call later on, experts from Vietnam, Indonesia, and the Philippines. And the second part of today's webinar will be about 40 minutes, where we will also include the question that you have, as the audience. So do not really hesitate to be interactive and ask your question during the presentation and during the panel discussion. But now, without further ado, I would like to give the virtual floor to my colleague, Dr. Arne van Stiphout. Arne, the floor is yours.
Thank you very much, Dimitri. And allow me to also thank our CASE partners for helping to bring this event to the different Southeast Asian stakeholders. So like Dimitri said, I wanted to give a presentation here that helps set us up for our panel discussion later. There'll be two parts that I'll be looking at today. So first we'll take a bit of time to review the Iberian blackout itself, the event, what happened, what we know at the moment as part of the ongoing investigation by ENSO-E, the European Network of Transmission System Operators for Electricity. And then we link this to broader implications for the energy transition and to some other work that Agora has also done on this topic. So with that said, let's start with this first part about the blackout itself and a reconstruction of what happened. Just to set the stage again, so it was on April 28th, so 3 months ago now, just after the middle of the day that the Iberian Peninsula experienced a blackout. And so the map shows the part of the European synchronous power system that was impacted. So within the Iberian Peninsula itself, there was a total blackout, and then there was a small part of France close to the border that was affected for a limited time. The rest of the system remained in operation as expected, and power itself was restored the next day in Portugal, so just under 12 hours after the event, and then a couple hours later in the early hours of the morning in Spain. Now, why did this happen? What happened? What went wrong? There are three phases to the events that lead to the final blackout. The first was that there were power system oscillations that brought the system in a less robust state. So just after noon, the Spanish grid experienced several low-frequency power oscillations in sort of two time intervals at different frequencies. And essentially what they did was to cause the overall voltage of the system to fall. So we see here in the graph this evolution of the voltage at the 400 kilovolt level in the transmission grid, where you see 420 kilovolts. This is the limit in Portugal, 435, this is in Spain, meaning to say that essentially below this level, everything should remain connected. This is the normal operating zone. The 0.6 hertz oscillation worth pointing out, it seems to, this is not yet fully confirmed, to have originated in a solar PV plant in the south of Spain, likely due to an operational anomaly. Now, the Spanish grid operator, they intervened to manage these oscillations. These are things that they commonly do, especially the second oscillation is a common occurrence in the European grid, or at least a well-known phenomenon. And they took these actions to mitigate this. But what this did, was to reduce the power system's ability to absorb further disturbances later on. And before getting to those, I want to paint a picture just as we're sort of passing after 12:30. So remember 12:30, 3:24, this is when the blackout happens. So we're a couple minutes out from the actual blackout here. And what we saw that at that time, over 70% of electricity generation in peninsular Spain, so just focusing on Spain here, was coming from solar and wind. You see there in the graph, the yellow, this is the solar, almost 20 gigawatts, another 3 to 4 gigawatts from wind. All in all, about 23 gigawatts of variable renewable electricity generation. And almost all the remaining generation came from synchronous generators. So these are generators that contribute to inertia. I will touch back on inertia right at the end of this first part. Spain was also exporting around 4 gigawatt and pumping 3 gigawatts. So essentially there was more production, quite a bit more than there was domestic demand for electricity. We get into the second phase. So as we said, the system operator had taken action to manage the oscillations and this decreasing voltage, so bringing the voltage back to a certain level. But then a couple of things happened that made voltage, which seems to be at the root of what happened, kind of turn into a runaway problem. So voltage control problems started happening after the loss of some sites. So what seemed to have happened is that as the system became more stressed, there were some distributed plants, including renewables, that were reducing their output as scheduled by the dispatch, but some others disconnected unexpectedly. And both of these had the effect of contributing to rising voltage levels. The next slide, I will explain why this was the case. Now, at this crucial moment, we have these initial trips, as it's noted there below, 2.2 gigawatt in 3 events. And this normally, especially the first one, should not be the cause for a system to fail. Transmission systems are designed to deal with failures, but the control measures that were supposed to be there to deal with these voltage issues, they didn't provide the voltage control that the system operator was planning for. And so what actually happens as a consequence of that is that the voltage continues to climb. So we see in the top right here at 12, the voltage levels. So this 1 is to say we're at 100%, we're at the nominal level. 1.1 means we're 10% above, which is the limit typically you should be still operating in a safe zone. So we see as we're at 12:32:58, just after the first generation loss, we see an initial rise. and then the bottom two ones are the second and the third right after them, and then we see that this voltage goes beyond the typical thresholds. And so what then starts to happen is that a cascade of trips caused by voltage issues is set off, because as each power plant disconnected because of the way voltage control was managed in Spain, it actually led to a further increase in voltage, which then caused other plants to experience over voltage or a voltage to that level that they in turn disconnected, and a cascade like this was set off. Now, it's very important to point out here that this is something that is quite strongly linked, it seems, to how the Spanish transmission system operator had set up its way of controlling the voltage. The key message, we think, is that renewables could have actually helped to stabilize the system, but they were constrained by existing technical regulations to do so. So on the left first, thinking at the conventional generators, these were the ones, so we're looking here under Spanish rules, nuclear, coal, gas, and hydro, that have to support the grid by adjusting the voltage independently from how much active power they're producing, what we will call dynamic voltage control. On April 28, there were 10 of such conventional plants that were scheduled to provide this service, which the Spanish government itself pointed out was actually the lowest number all year. So there are some questions there. Did the TSO provide enough resources or schedule enough resources? But not just this, the other factor that was key is that some of these plants, even though they were contracted and paid to deliver this voltage control service, they actually failed to respond adequately when the disturbance happened. So they actually didn't manage the problem, and some of them disconnected before we reached this 435 kilovolt level, and thereby made the problem worse. On the other side, we have renewables, and they fall under another kind of regulation in Spain at the moment, which means this regulation stipulates they have to provide the more limited static voltage support. So this is to say a fixed power factor or a fixed ratio of active and reactive power. Reactive power is the part we use to manage voltage. And what seems to us have happened is when they first decreased their dispatch, as they were scheduled to, this meant less reactive power absorption, which meant increasing voltages as a consequence thereof. And then actually there were also some issues with some of the plants to deliver this fixed power factor, which made this problem worse. There was even less reactive power absorption for the plants operating at low active power levels. So again, higher voltages. And all of this together is actually the main thing that we want to underline here is that this fixed power factor, this static voltage support, there is no reason to limit these plants to this. These plants are technically capable of providing the more advanced dynamic voltage support, but current Spanish regulations do not allow them to do this. A reform that the TSO had proposed to the regulator to change this had been pending since 2021 and is now to be implemented in 2026. So what we see here in part is both grid operating practices, but importantly also policy and regulators, policymakers and regulators, not actually keeping up with the changes of the power system that is happening and the consequences this may have. The final stage, and I said there were three, the third stage was the actual runaway into blackout. So even though it wasn't a frequency problem initially, because of these cumulative generation trips, the frequency starts to fall because there is a shortage of supply now. And the system operator has automatic load shedding defense plans that were activated to try and manage this. But it wasn't a frequency problem that was underlying it, so these things didn't work. In fact, they made things worse because as you shed load, it typically further increases the voltage. The France interconnection that was exporting earlier to France is now at its maximum of import. And because it's at its maximum, there is this loss of synchronism that is starting to happen with Europe. This line gets triggered and disconnected. The lines to Morocco and Portugal as well. And eventually we see here the red line, which is the voltage that after 12, 16, 17 goes beyond the limits and then drops, and we see that frequency drops with it. And at 12:33:24, we are in blackout. So this is the sequence of events. A final word on this first part dedicated to inertia. This was the thing that a lot of commentators jumped on, and it seemed because there was so much solar and wind in the system, and everyone seems to know that that means that these plants, they don't provide inertia, so probably it was an inertia problem. It seems that this was absolutely not the case, and the Spanish grid operator has even strongly denied that this was the problem. It's a voltage problem, not a frequency problem. Inertia was not the problem. The grid operator had assessed the risks of low inertia operation in its transmission development plan, and they had determined, as is there in the footnotes, and if you want, you can read it in more detail later when we share the slides. It had assessed what kind of capacity needed to be in the system to manage the inertia, and it seems with this 30% of generation that was online to provide inertia, that this level was consistent with past stable conditions, and in fact, actually, the power system had recently operated reliably with even higher shares of renewables and less inertia providing generation. So inertia wasn't the problem, it was a voltage issue that wasn't managed appropriately. So with that set as the stage of what happened in Spain, we want to take a little step back and see what does this mean going forward for the evolution towards power systems with more renewables, and how grid operators and grid operations have to adapt to this new operational reality. Very big context picture here to say is that while big blackouts are rare, they do happen. On the left, you see a graph with the 20 biggest blackouts in 2000 to 2025. You see the Spain and Portugal one highlighted there. You see there have been bigger ones as well in this last 25 years. But so you see, it happens. And when it happens, this is what we see on the right side. Very often, the issue is related to grid infrastructure and the practices around operating this infrastructure. What this points to, we think, is that as power systems evolve, so must approaches to power system reliability, with a particular focus on power system stability. So first part here is that power systems are entering the era of power electronics. Existing security and stability paradigms are not really fit for purpose anymore because they are built around the idea of a power system that has a few very large, typically fossil fuel powered power plants. Now, new practices will be needed as we go to a power system that is increasingly built on inverter-based resources, such as solar, wind, but also batteries. And that particularly growing electrification makes this shift even more urgent because the consequences of any partial or full blackout will be more severe. There are also broader system trends to place this in. So we highlight a couple here. As we go to more inverters, it typically also means a more digitized, a more interconnected system. So things like cybersecurity become of more concern. If we have a more changing climate with more extreme weather, this is also important. Think, for example, about how ambient temperatures can affect the amount of power a transmission line can safely carry. We have a more decentralizing power system, so there are many more assets to manage for the system operators, which, that's an operational challenge. On the other hand, there is a chance for enhanced reliability because if your resources are more spread, you can operate more safely in an islanded way or keep the problem more locally contained. And of course, there are benefits related to energy independence. But moving to stability specifically, what we want to talk about in the next couple of slides and in our discussion is that it is perfectly possible to run an inverter-based resource-dominated power system in a stable and reliable way. There are a couple of things that need to happen for this. First, we have to accelerate grid modernization and grid development because new infrastructure will also be needed. So this will come up in the next slides. And we need a new approach, particularly to practices around system stability. So this is on the one hand thinking about quantifying these needs, because a lot of system operators only recently have started thinking, for example, about how much inertia a system needs. And also on the side of the services. How do we source these services in a way that ensures reliability, is cost effective, and encourages innovation? And those three things is what I want to go into a bit more detail now. As seen in South Australia, we actually think, these blackouts can be critical wake-up calls that drive upgrades in grid infrastructure and practices in line with ambitious goals. So just to say, in 2016, South Australia experienced a really big blackout, which affected just under 1 million people, where extreme storm weather damaged 3 high voltage lines. This caused a couple of very short-lived voltage dips, but those dips were enough to trigger the voltage protections of 9 wind farms, which reduced the output of these wind farms. This reduction caused a significant increase of the imports over the one interconnector that South Australia has to the rest of the eastern South Australia or Australian power system. This interconnected overloaded, it tripped, the system got islanded, and there was a structural shortage of supply, and it collapsed. And what did the investigation show at the end of this? That these conservative settings, or that the wind farm protections had been set in quite a conservative way. They could have remained connected, but they were told not to. So another example of regulation not really keeping up with the new realities of the power system. It also showed the need for more interconnection with New South Wales, because also that could have contributed to keeping the system online. And in particular, we see these new solutions coming on. So the operators thinking about how much inertia they need and adding several really large batteries to deliver some of these services. And what we see in essence is that in some ways, this is a real success story, because today South Australia is a leader in the clean energy transition. So in 2024, 72% of electricity generation, net electricity generation, I should say, in South Australia came from solar and wind. In 2021, already at the end of it, it met 100% of its operational demand with variable renewables for the first time, and now regularly does so at 100%, and has set itself a target to hit 100% renewable electricity generation by 2027. South Australia is very much not the only place where we see these kind of trends and this kind of leaning into renewables and still operating systems in a very reliable way. So a couple examples here you see with different sizes on our x-axis going to larger systems, and the annual shares in the blue circles, and the instantaneous share, so that's to say in a particular hour, in the purple squares. So we see South Australia marked there, Spain is there, ERCOT. It's a smaller system, so even with a small annual energy share, it can have quite high instantaneous shares, but these systems are running are running reliably. So coming back to those 3 things that we think need to happen. First, grid modernization and grid development. So on grid modernization, what we think this shows is that efforts have to speed up to keep up with the evolving electricity supply and demand. So grid modernization, we're talking here about a couple different things. Advanced remote monitoring and control equipment is needed, including more and more down into the distribution grid as needed. We need to optimize the use of existing lines. So grid enhancing technologies are part of that, things like dynamic line ratings and so on. We need to update planning and operation practices, including a deeper integration between transmission and distribution. More and more of the generation will be in the distribution. A transmission system operator has to know what's happening there to be able to run the system well. And we need clearer mandates and incentives for grid operators and regulators to plan proactively for these future grid needs. So not just at the transmission level 10 years ahead, at the distribution level, sometimes even shorter horizons, but really thinking, what is the trajectory to a net zero power system? What do I need to do with my infrastructure and my operations to make that possible? And then, of course, as so often with the energy transition, this also means investing in workforce and digital tools to help this happen. The grid development component of this first part, also something to underline, that stronger grids with well-designed and well-managed interconnections are a part of reducing the risks of blackouts and generally improving reliability. Interconnection benefits, I assume, are well understood by the people attending this webinar. Just want to underline here that in the example of Spain, they were well below the interconnection targets that the EU had set. So only 4.4% of its peak versus the recommended 15%, and stronger links could have enabled more robust support from the rest of the system. Also worth pointing out that the interconnector between France and Spain played a crucial role in restoring the system by providing black start power to the Spanish system. And maybe one thing to highlight that, of course, increased interconnection can add operational complexity. So a good coordination between operators is needed for things like operational risks or complexities, cybersecurity risks. Generally, though, the benefits really outweigh the challenges. These challenges are simple technical challenges that can be addressed. Second point, looking at the stability needs. So the need part of how do we start quantifying actually the kind of services that we need. So transparently defining what those services are, the different types of products you might say, and then quantifying what a particular power system needs. That is a way for system operators to remain on top of this transition. So there's a couple mentioned here: frequency stability, rotor angle stability, voltage stability, which was the one of concern in the Spanish case, and also resonance stability. So we have all these different controllers and inverters. How do they behave nicely together? And so we say that what is needed here is for operators and regulators to conduct and report as well on regular, transparent assessments of stability's needs, where the real trick is that if you overestimate the needs, you can induce extra costs and delays for renewable integration and electrification. But of course, also underestimating them could give issues with grid stability. And then if you can clearly quantify these needs, you can start to target your procurement, identify gaps in your system. And again, underlining that in these assessments, we should look ahead at, for example, a 100% renewable future or a net zero future. Thinking about the supply side then, 2 points we would like to make. First, it's very crucial to strike the right balance between universal requirements and remuneration for the sourcing of services. So if we look on the one end, requirements, you can set requirements for all technologies or for certain groups of technologies that they need to have certain capabilities or that they need to provide or be capable of providing certain services. If you do that, there can be risk in it. I will go into one example a bit more on the next slide. On the other hand, we have service markets where it's actually more voluntary. Maybe you still ask a certain capability of some players, but then participants bid into the market, and then you might get, and it might just be a procurement, doesn't have to be a full market necessarily, a targeted procurement again, but that might give you access to cheaper services, particularly if this also means opening things up from just a couple conventional technologies to the whole sweep of technologies, which is what the second and final point on this is that I'd like to highlight, is that different technologies can provide different stability services that an effective sourcing approach can target. So I won't go into particular detail here. This is a table that's part of one of our reports that you can review if this is of interest, but you can see that particularly batteries, they don't have to be grid forming for all services, but this is another concept that has come up a lot. But batteries already, they can provide a ton of services. Variable renewable energy themselves, it can provide a lot of services. But then there are a couple things like asking a battery to be grid forming and to provide thereby synthetic inertia. This is quite common and in practice already in several places. Asking renewables to do this might come with other challenges. For solar, there aren't really inverters at commercial scale available yet in practice that we see today. For wind, it might even have implications for turbine and blade design, which could drive up the cost of those wind farms and just would not be necessary. This is introducing these additional costs and delays that I mentioned earlier that are best to avoid. Ending on two good examples that we want to highlight. So UK approach to guarantee grid stability while integrating high renewable shares. So there was the System Operability Framework and Stability Pathfinder initiatives. I won't go through the different things, but you see here things like location-specific stability requirements, giving long-term contracts for services so that market operators can respond to them, can anticipate the needs and know that it's worth making the investment in this. And that's these transparent signals that follow from this. Another example that we think is good practice is what has happened in Germany, where there are these, where there is this mandate for regular assessments of all dimensions of system stability in the energy legislation. So the TSOs are now required to submit a system stability report every 2 years, where they look at the current status. They identify needs and gaps for secure grid operation, including this look ahead at 100% renewable generation. They quantify the needs for the next 10 years and then evaluate and compare concrete options to meet those needs on different dimensions and come forward with at least one path with actionable steps to get to this place. And then these things feed into the system-wide strategies that are in Germany's system stability roadmap. If this is the kind of thing you want to learn more about, we did if I might say so myself, a very good report about this only last year. So below you'll also see the links for the webinar or just the key findings, but also the full report. 4 things that we pointed to here. One, a successful transition requires a new approach. This is what we've talked about over the last couple slides. We think too that to make informed decisions for a renewables power grid, it is important to clearly quantify the system stability needs with transparent methods. An optimal approach to stability should focus on using the most cost-effective resources at the relevant location. A lot of stability things have a locational element, so it's important to consider that. And then also a comprehensive dialogue among system operators, manufacturers of generation and storage, and relevant authorities is critical to identify the best solutions. So this example of implications for wind turbine design, for example, is a place where the communication between OEMs and utilities and public authorities is of importance to avoid making decisions that have unintended consequences. And with that, I want to wrap up with just a repetition of the key findings of what we've just talked about. So the Iberian blackout really put a spotlight on reliable electricity supply as Europe transitions to climate neutral power systems. This is not something people did not know about. People that pay close attention to the power system transition know that coming or bringing in a lot of these inverter-based resources means that there is a transformation needed in how we operate the grid. And if you do that transformation successfully, renewables can be part of the solution of helping to stabilize the system. But in Spain, we saw that regulations did not keep up with this new reality. And so there underlines the efforts or the need to accelerate the efforts to align stability frameworks with the new operational reality. Very important also to highlight that it has been done, it is being done, this is perfectly possible. There are several renewables dominated power systems that are already operating reliably across the world. You see countries like Denmark that are part of a bigger synchronous area, but there are also island countries like Ireland or things like South Australia that are, while now better interconnected, still on the end of the Australian eastern grid, that operate with very high instantaneous variable renewable energy shares, and that use some of these new services that they've defined, like fast frequency response, synthetic inertia, voltage support, and so on, to actually manage this situation. And then just to repeat the 2 or 3 points that we said at the end, grid modernization and development must accelerate to keep pace with these changes. So the stronger connection between the Iberian Peninsula and the rest of the power grid was one of the things that could have helped manage the situation and maybe even avoid the severity of consequences that we saw. And so infrastructure planning and investments must advance in parallel with the regulatory reforms that enable more flexible and proactive system management. And then system stability requirements must be transparently quantified and services optimally sourced. Just reiterating again that there are changes that need to be made here, and there are also here good practice examples out in the world. So UK's inertia needs assessment we talked about, fast reserve auctions as we see in Texas and Australia. The EU, there we see the ongoing network code revision, which is an opportunity to support the integration of stability technologies like grid forming solutions. But as we said, the one of the key things here is striking the right balance between universal requirements, which may be overburdensome and introduce unnecessary costs, and the remuneration for the sourcing of these services to also stimulate innovation and let new technologies really play the role that they have the potential to play. So with that, I want to thank you for your attention and pass it back over to Dimitri for perhaps some initial questions on this before we move to the panel.
Thanks a lot, Arne, for this very clear presentation. You managed to actually bring some of those very technical concepts in a intelligible way. So I thank you for that. And indeed, there is 2 questions from the audience that I may bring to you already right now before we move then to the panel discussion. The first one is, you mentioned the role of interconnection to contribute to enhance system reliability. But the question is, what about decentralized power system? Can they also improve reliability, and how these 2 levels interact?
Yes, very good question and well worth highlighting. Absolutely. So the idea is we can have inverters that are capable of providing a range of services. They don't have to be grid forming for this even. A lot of things like voltage support, they can provide without being grid forming. There are additional services like the provision of inertia and these kind of frequency control mechanisms that they can provide if they are grid forming. So essentially, what this means is that you will have your resources more spread out. Instead of having one big plant in one position somewhere providing inertia or voltage support, it will be spread throughout the system, which in some ways can actually be a benefit for managing some of these stability phenomena like voltage that can be much more local than an overall system balance. And as I said before, it also means if you lose a unit, it's probably a smaller unit because it's not a big plant. It might be a smaller solar or wind plant. And if you have issues in one part of the system, it may not need to cut off whatever resources are there, like a big plant for the rest of the system. So you might be able to manage the rest of the system more easily with this way. So absolutely, thinking about these things in this more decentralized way and leveraging the opportunities that these decentralized technologies provide is a key piece of the puzzle here.
Thanks a lot, Arne, for that answer. A second question is related to this frequency oscillation. And the person in the audience is asking, some reports said that it was maybe due to the large distance in the European grid. So basically the oscillation starting somewhere in the Baltic state and then reaching all the way to Portugal. Do you have any view on this? Can you comment what exactly happened and what this oscillation were all about, especially this frequency level that you mentioned was actually quite unconventional?
Sure. I'll caveat whatever I say here to say this is really a topic for actual grid experts. This is quite complicated grid physics. At a high level, what I understand is that in a large interconnected system like Europe, you will have these kind of oscillatory phenomenons. So the second oscillation at 0.215 hertz, this is one of the, I think they call it the east-west mode in the European system. It happens every now and again, and system operators know how to manage it. They know what kind of actions to take. So, for example, they might mesh the transmission grid more to manage that. Could it have started in the Baltic states in this particular case? Because that's indeed kind of the access Baltic states to Iberian Peninsula. It's unclear. What seems to maybe have been the case is that part of this was this 0.6 hertz. This second oscillation of 0.215 was preempted by a short 0.6 hertz. So maybe there was something about this area around this PV plant in Badajoz that set it off. But for this, we still wait for the ENSO-E investigation to have more conclusive data on causality.
Thanks a lot. And with this, I will close the first part of our event today. And Arne, you stay with us in case there is additional question. And I would like to call the panelists now from Vietnam, Indonesia, and the Philippines. I will start with Mr. Duong Man Quang. Mr. Quang is a senior energy advisor at the GIZ Energy Support Program in Vietnam. Mr. Quang specialized in legal and regulatory framework, also technology cooperation to promote the energy transition in Vietnam. Prior to join GIZ, Mr. Kwong spent 10 years working with various state management authorities under the MOIT, so the Ministry of Industry and Trade, in the energy and electricity sector. So it included places like ERAF, the regulator, Electricity Regulatory Authority of Vietnam, but also the General Directorate of Energy and the Electricity and Renewable Energy Authority. So we are very pleased that you could join us today, Mr. Kwong. The second speaker or panelist I would like to bring is Mr. Kevin Marojahan from Indonesia. Dr. Marojahan is a lecturer at the Institute of Technology Bandung. He holds a PhD in electrical engineering from the University of Grenoble and specializes in local grid stability to integrate high shares of variable renewables. He has also a research position at the G2 Lab and Schneider Electric in Grenoble, where he assesses microgrid stability through real-time simulation models. Thanks a lot, Dr. Marojahan, for joining us today. And last but not least, I would like to call Mr. Bert Daludsung from the Philippines. Mr. Bert has been already in some of our webinars. We're really happy to have him again today. He has 40 years of experience in the energy sector, so very long-lasting experience with particular focus on energy project development, national energy planning, and policy formulation. He's currently the Energy Transition Advisor of the Institute for Climate and Sustainable City, ICSC, which is one of the partners of this project, and the Director and Chief Technical Officer of Preferent Energy INC. Bert served as a Director for Energy Planning in what now is known as the Department of Energy, DOE, in the Philippines. And during that time, he was involved in pioneering work around geothermal, electricity cost structure, pricing mechanism, national energy balance reporting. Bert is currently the chairman of the Biomass Renewable Energy Alliance, BREA, and was previously appointed as a member of the National Renewable Energy Board. So I'm very pleased to have such an expert panel with us today. And I would like to start maybe with Vietnam. So Mr. Kwong, and why Vietnam? It's because out of the three countries that we have gathered today, Vietnam is the one with the highest share of actually wind and solar power. And it is known that the grid development has also been a bottleneck in the last few years for the continued development of renewables. So my first question to you, Mr. Kwong, would be actually two questions. The first one is, in the public discourse in Vietnam, did anyone comment on the Iberian blackout? And if so, in which sense? Was it basically used in the debate in Vietnam? But then, most importantly, where do you see the situation in Vietnam now when it comes to grid development? What are the biggest challenges that you see for that development?
Thank you, Dimitri, for very interesting question. So, yes, very concrete answer is yes. We are very concerned about the recent incident in Spain and Portugal. So about the blackout. So basically, we see the potential incident that can be happen in Vietnam if we have the same, let's say, interconnection and also the same share of renewable energy in the future. So there was a lot of discussion and also about the concern from the state management authority. So we GIZ even received the ad hoc request from, let's say, from MOIT, the Vice Minister, asking if we can conduct the proper study on what should be the potential impact of renewable energy in the future, let's say, with the context of very ambitious target in the PDP8 revised that we are aiming to, let's say, more than 30% in 2030 and more than 70% in 2050. So which means very ambitious. And it with that context, it can be happen anytime in Vietnam if we don't prepare well and with a very, let's say, proper planning. And yeah, so we also foreseen the potential negative impact if the system didn't work well. So let's say we faced the congestion back in time in 2024-21, but it was, let's say, because of the transmission line haven't been invested in a timing manner. So but now we more or less solved it because the the investment is somehow slowing down, and the transmission is now go online, and then the completion of the construction. So I would say no more serious congestion in the transmission line, in the transmission grid. But we foreseen very serious impact if, let's say, for instance, if we reduce the fossil fuel traditional power plant, we can provide the rotating mass, and then in the future we can have, let's say, lack of inertial, and also impact of voltage support and frequency control and so on. So yeah, so given that fact, we are, let's say, uh, planning a lot of things in the worst for the worst case. Let's say we upgrading the grid code time to time, tighten the requirement for of the renewable energy connected to the grid, and also uh, taking into account the emerging technologies that can support the flexibility of the grid.
Thank you very
Yeah.
much. So it's interesting to see that in Vietnam, you take steps indeed, especially on the transmission level, for basically modernizing the system, also in terms of, you said, revision of the grid codes. What about the distributed part of the grid? Um, we saw that in the specific case of the blackout in Spain, they may probably also have issues related to the local level and also diffusion of the issues to more system level. How is it happening currently in Vietnam? Could you tell us a little bit more this also coordination between the distribution grid and the transmission grid? Is it perceived as a challenge, as a problem for the development of renewables?
True. We also face the distribution network challenges when we have, let's say, booming of rooftop solar system, which is in the decentralized area. So we have overload, and the power backward revert from the distribution network to the transmission network, which is not really designed for that scenario. Yeah. So traditionally, the transmission network, the grid, let's say, the grid designed for generation to transmission, and then down to the distribution network. But now, with a lot of decentralized resources like rooftop solar, the power will go back to the transmission, and then the transformer will be overloaded somehow, and also the power quality will be impacted. And so it was because of the let's say, uh, attractive feed-in tariff for rooftop solar, and then a lot of investor and a lot of household building, they deploy a lot of rooftop solar, and then we face that very serious in just 1 year, in 2020. And then a lot of discussion and initiative that bring up to show that problem. For instance, we bring the TSO and DSO together, and then they have the coordination agreement that to exchange the information, and to let's say, to optimize the power flow from transmission and also distribution network. So by doing that, we, to some extent, we can solve the problem. And also TSO, they are thinking and planning to deploy the DERM, which is the distributed energy management system, that can allow them to monitor and control the distributed network more, like optimally. and
Mm.
and also we are we are thinking also about the V2G solution, so vehicle to grid, and then we can take advantage of decentralized battery from, let's say, from vehicle. But still, we still need to conduct a purpose assessment if there will be any impact to the vehicle, and also impact to the grid and the lifetime of the equipment. Yeah.
Thanks a lot. Very clear, Mr. Kwang, for the answer. Allow me to move to Indonesia. Mr. Marojahan, Dr. Marojahan, Indonesia is not the country with the highest share of variable renewables in the region. Development in PV are quite slow compared to global standards. But still, I would like to ask you first the same question. Is the blackout in Spain, or was the blackout in Spain discussed among experts? And in which sense was it used to say we need to take radical measures to stop renewables, for example, or we need to adjust our practices of grid operation and planning? This is my first question. And the second is, in order to go toward this long-term vision for Indonesian decarbonization with 2060 goals, how the grid modernization agenda is brought forward to ensure that the country can meet its climate mitigation ambition?
Yeah, thank you very much for those two questions. So first, about the Iberian blackouts. Sure, it is widely discussed and spoken also in Indonesia. But as you know, Indonesia is divided into several synchronous regions. So like Java, spanning across, let's say, 1,000 kilometers, one synchronous area. And then we have like 4 or 5 more bigger synchronous areas, and then we have a lot of smaller ones. So when we talk about these Iberian blackouts, mostly we talk about the lines of defense. As you know, the first lines of defense would be the reliability of our power systems, the adequacy of our planning. The second one is the protection, and so on and so forth. So normally we will talk about those lines of defenses, because in Indonesia we also experienced some minor blackouts over the past 5 years. So let's say in Sulawesi, North Sulawesi, last year, and also in Bali, only in Bali region this year. So mostly we talk about that. So yeah, uh, about those lines of defense, actually sometimes it occurs that the blackouts in Indonesia is initiated by uncleared faults. As you know, normally for a fault to occur, we have to have a really good protection system to clear the faults. But in Indonesia, sometimes we have a failure to clear the fault. So this is mostly why we experience blackouts. So about the renewables, especially inverter-based generations, actually one of our synchronous systems in Sulawesi, southern Sulawesi, we have quite good share of renewables, and right there the grid is very modernized. So they have like good protection systems, SCADA, real-time monitoring. But in grids with lower renewable share like Sumatra, mostly the efforts are taken into modernizing the transmission systems. So Sumatra, spanning across 1,700 kilometers, we at the like 5 or 10 years ago, we only have 150 kilovolt transmission lines. So we have large oscillations actually in these regions. Nowadays, we try to modernize it with 275 and 500 kilovolt transmission lines, so that the power transfer can be much better. And actually, we are talking to installing more and more renewables, but mostly I think the renewables that we are talking about is mostly hydropower, because looking at the wind and solar, I think the cost, sometimes they say that the cost is higher than the other types of generations. As you know, in Indonesia, our market is still very regulated, and to increase the electricity price is very, very difficult. We have to get the approval of the House of Representatives. So well, let's say in Indonesia, the grid transformations in facts like statcoms, SVC are very slow. Normally, when we talk about grid modernization, it will be about installing more real-time monitoring and then transmission lines, but not about the facts and other things. So yeah, that's what I can share about the updates in Indonesia. So with regards to decarbonization, yeah, that's what I said. In Indonesia, actually, the load curve is very much different because our peak load is at the night time. At the daytime, normally our load is very low. That is why if we install more PVs, then we will have lower loads in the daytime. And we have a lot of base loaders such as geothermal, also coal-fired power plants, and they cannot work properly in a lower loading, and they will have a very bad efficiency. So that is why normally with regards to decarbonization, they will talk more about co-firing. So coal-fired power plants, we give them biomass, and then they talk more about the run of river hydropower plants, or they talk about the more stable ones, such as the geothermal. But in our recent PLN is our utility business planning. Actually, I think we have a quite good plan on installing more renewables, such as solar PVs and also wind farms.
Yeah, thanks a lot, Dr. Marojahan. And indeed, I mean, the challenge that you mentioned regarding covering the cost when the system is regulating prices at a pretty low level, and also the question ultimately of this duck curve, right, which is happening when the solar PV is capturing part of the market in the middle of the day, are challenges that most systems in the world are also facing. I find it interesting that you say in the new vision for PLN and Indonesia, there is still a willingness to develop more of these variable renewables. I come back to the question, how is it in your view aligned with the grid modernization plan? Because a grid is in principle technology neutral, right? But effectively it is not, because you design a grid differently depending on the type of mix of resources that you plan to develop. And Indonesia has planned large grid development between islands. Could you reflect a little bit of this from your perspective? Is the grid planning fit in the long run for renewable energy development, or is it more pursuing other type of objective when it comes to power system development?
Yeah, actually, when we talk about the grid planning in Indonesia, normally the objective would be to minimize the total cost, and normally the renewables will be like not really the main objective. So we try to comply with like government targets to increase renewables, but as you know, Indonesia has already a target to become carbon neutral in 2060, if I'm mistaken. Also, we have a target of energy mix, but please bear in mind that in Indonesia, the energy mix is reflected from the primary energy mix. So in order to achieve like 50%, it's quite difficult, because from thermal power plants such as coal power plants, the efficiency is like 33%. So it's quite difficult to achieve our energy mix target actually in Indonesia. So but yeah, so that is normally our objective, to minimize the total cost. That is why normally when you make a competition between thermal power plants also and renewables, also you do not put like any more competitiveness on the renewables, such as carbon prices or carbon tax. Naturally the thermal power plants will win. So that is the case in Indonesia. But sure, with regards to renewables and our grid modernization in Java, Bali, they are installing a new operation center for our transmission system operators. So this will have more better view on our grid monitoring. So we will have a better reliability in Java, especially. Also, they are also planning on interconnecting our synchronous systems, such as from Sumatra to Java, and also Sumatra to Batam and to Singapore. So I think sure they are planning as well to modernizing our grid.
Thanks a lot, Dr. Marojahan. Let me move to the third country today, the Philippines, Mr. Beat. First, similar question to the two other panelists. which impact the Iberian blackout had in the public discourse, but maybe also the policy discourse regarding renewable energy development in the Philippines. And my second point is the Philippines is pushing quite a bit of renewable resources. And lately, there is also this important hydropower plan. Could you tell us a little bit how this basically mix decarbonization, mix discussion in terms of capacity development in the Philippines is linked to also the question of grid modernization? So how these two aspects are actually planned? Are they really much integrated? Is the renewable portfolio following the grid, or is the grid following the renewables?
Yes, thank you very much, Dimitri. Before I answer the question, let me thank Arnie for his very clear and succinct explanation of the Iberian blackout. I think you asked about the discussion in the country regarding the Iberian blackout. It was discussed, and there were those who, without the benefit of the information that we just heard, have assumed that it was because of too much renewables. Therefore, we need more batteries every time we implement solar PV projects. Obviously, that's not the case, as we heard. It's really a complex problem, and renewables are not the core problem of the Iberian Peninsula. So, first of all, I think that it will be very useful for the Philippines to learn from the Iberian Peninsula discussion and analysis. Today, we only have about 4 to 5% variable renewables. Most of our renewables come from hydro, various types of hydro, storage, run-of-river, pump storage hydro, and geothermal. So a lot of our renewables are, they have inertia, no problem with having more of those. But in the latest long-term energy supply scenario that is continued to be done by ICSE, we see that the future is really more solar and wind. Even if we have competitive geothermal facilities, for example. The reason is, unlike Indonesia, we import most of our coal from them. They do not have to import their coal. We are subject to international prices and supply disruptions. Now, based on our analysis, if we look at the current inventory of power plants, we have a lot of coal-fired capacity. In fact, a lot of our capacity would have to be cycled daily because we have too much capacity and not enough load. Unlike Indonesia, we have a twin peak, one at noontime and the other in the evening. So solar works, I think, better for the Philippines than it does in Indonesia. And recently, based on the World Bank study, we have 170 gigawatts of offshore wind. The Philippines has always started large-scale renewables in Southeast Asia. We did that, I think, with geothermal, solar, wind, even pump storage hydro. We were the first to implement those. So all of this, like I said, we just did a long-term energy supply scenario. It's pointing to the least cost coming from solar. And of course, we have to add energy storage and all of the other renewable energy that we have. But I think based on the lessons from the Iberian Peninsula, we can say that apparently we can have 50% renewables and still operate with high stability, system stability. This is consistent with the study that was done about 9 years ago in Luzon and Visayas, in the Luzon and Visayas grid. That study said you can have up to 50% variable renewables in Luzon and Visayas and still have stable operations. So the result, the current analysis presented by Arnie is aligned with that previous study. So from where we sit in the Philippines, I think that our government has targeted a reasonable target, 35% renewables. by 2030, 50% by 2040. I think these are achievable targets. You know that in the Philippines, everything is private sector. All of our power plants, large power plants on the grid are built by the private sector. Our system operator is private. Our distribution utilities, around 150 of them, are all private. So we have to work very closely with the private sector, come up with a unified plan that everybody buys into. And I think so far there is alignment in the government and private sector's view on the expansion of the Philippines, an expansion towards the energy transition that I've just discussed.
Thanks a lot, Sir Bert. Just to come back to the question of the grid, then as a underlying infrastructure for this capacity change in the generation. Do you see specific bottleneck? You said it's all private investment, but what about the regulatory changes that may be needed to accelerate the grid development? Or do you feel like the grid infrastructure in the main island of the country is already robust enough? Or do we need major investments to reinforce the grid?
Well, I think that grid access is always the most, the most challenging part of power development in the Philippines. So it's not a problem that has been solved. It is always a challenge. I think what I'm seeing is that there is now a better alignment of the power development plan with the transmission development plan. And if we continue to do that, if we continue to expand our systems in time, that has always been the problem in the Philippines. Delays in transmission expansion. I think we're catching up, but a lot of work remains to be done. So I think that if the government and the private sector truly work together, and the private sector is different kinds of private sector. Private sector doing the power plant, private sector doing the transmission, and the other private sector doing the distribution. So I think all of this have to be aligned. And, we have a new set of officials just recently announced in our government. So I think it's a challenge for them. And as far as ICSC is concerned, we have the ability to work with them very productively.
Thanks a lot, Sabert. I would like to come back to Vietnam and with a specific question related to stability. You mentioned, Mr. Kwong, the need to have a specific services to basically operate the system. I would like to understand better if there is a business case in Vietnam, because in Vietnam there is a lot of now market segments which are also open, right, to basically non-state monopole part of the system. What about renewables or battery storage? Are they allowed in Vietnam to provide some of those stability services like voltage control or frequency control? And if they are, what type of mechanism remunerate those services? Arne in his presentation was showing that there is, this trade-off between coming with requirements of the services or the other part being more coming with remuneration of those services. So how is the discussion in Vietnam in the context of the broader market reform which is ongoing?
Yeah, thanks, Dimitri, for the question. So to answer about the renewable energy first. So basically, and technically, they are capable to provide the ancillary service like voltage support and frequency regulation also. But they are not getting paid by providing such kind of service. They are mandated, they are obligated to let's say to be controlled and in order to provide the voltage support at the grid code set. Yeah. So and also in the upcoming times there will be no service will be asked and get paid to the renewable energy. But for since they will be enjoying the fixed fixed price after negotiation with the state-owned enterprises. But for the battery storage, for the time being, we the legal framework for providing ancillary service is not available. But we expect that it will be in place in coming times, let's say months, because we in the PDPS revised, Vietnamese government, they plan a lot of battery storage capacity and also pump storage and, let's say, energy storage system in order to support the stability and flexibility of the system when we have less traditional fossil fuel synchronous power plant and more inverter-based resources like solar and wind and windmill. In coming years, we need a lot of battery storage and pump storage. And of course, in order to, let's say, attract the private sector to pour money on investing, deploying just such systems, there will need to be some pricing mechanism and also kind of proper contract that allow them to recover the investment costs and also to gain the, let's say, reasonable profit. For the time being, a lot of discussion and a lot of support from different donors to bring the experience and also recommendation to the government of Vietnam to have better understanding and before setting the proper mechanism and legal framework for such kind of ancillary service. And we expect that it should be available very soon.
Well, thanks a lot, Mr. Quang, for this answer. And so the pragmatic approach that Vietnam is pursuing in this context is quite remarkable, I have to say, in terms of like investigating which part of the market needs to be reformed and how. Let me move back to Indonesia again. And I would like Mr. Dr. Marojahan ask you, you mentioned that in some specific islands or a specific part of the system, there were already in the past some blackout. You mentioned specifically northern Sulawesi, if I didn't mistaken. But you also said that in this island specifically, there is also now a better grid infrastructure which has been put in place. I would like to get a bit your view on this question of stability, especially looking at islands. We have seen from Arne that there is example in countries, island countries, which with 100% renewables, right, in very small system. What are, in your view, the most urgent reform needs? Maybe also illustrated by the experience that has been with blackout in Indonesia, but what is happening on the stability front in the way grid code are redesigned, in the way stability assessment are performed? Is there some development that you see which would also be allowing the country to move to higher share of renewables?
Yes, thank you very much for your question. So basically, Sulawesi is actually divided into two synchronous regions, the northern part and the southern part. And the one which experienced blackout is the northern one. The southern one is more stable because the southern one, if I'm not mistaken, the peak load is much higher, about 2 to 3 gigawatts. The northern one is much lower at 400 megawatts, 500 megawatts. So actually, if you ask what about the renewables, actually in this region, renewables are quite prominent. In the northern one, we have quite significant hydro, some PVs, also geothermal. In the southern one, mostly wind farms. But energy-wise, I don't think it's quite significant. But capacity-wise, I would say it's quite good. So why you say actually in Indonesia we have in the capacity expansion planning, our criteria of reliability is only loss of load probability of maximum 1 hour per year. Sorry, 1 day per year. 1 day per year is quite high with respect to the American standard, because in the US, if I'm mistaken, they have 0.1 day per year, so 10 much lower than what we have in Indonesia. So actually, operational wise, it is quite difficult to have like forced outages in Indonesia, because then we will have insufficient reserves, either cold reserves, hot reserves. Normally, that is the main problem, and this is also why it is quite difficult to absorb renewables, especially variable renewables, because we do not have, quite good amount of reserves. And once we have forced outages in our generating plants, then it's very difficult to keep the stability. So that is the main reason. And also in Indonesia, as what I said, mostly the grid is, or the power system is very regulated. And with regards to the valuation, mostly the valuation is on the kilowatt hours, the energy only. So similar to Vietnam, the ancillary services are considered mandatory, but not very monitored in real time. So sometimes some generators say that, okay, we have a black start capability, or we have this frequency regulation capability, but it is not monitored in real time, especially in the smaller synchronous areas. So that is why we are more prone to blackouts. Yeah.
Thanks a lot. Very clear. Sir Bert, I will ask you a last question, and then I will finish with a closing question to all of the panelists. The question to you, Sir Bert, is which important regulatory change you see as needed to reform this kind of stability provision in the Philippines? And which role do you see for battery storage specifically to provide those services? Do we have the adequate, basically, regulatory environment for that? Or is it an important reform which needs to be tackled by the regulator?
Yes, thank you very much, Dimitri. I think we have the proper regulatory framework for that. I'd like to believe, based on the most recent analysis presented here, that we should review our grid code and maybe find out how they can be improved so that we are prepared for more inverter-based power supply sources in the grid. I think that there is a need to match the new capacity with future regulatory planning and operating parameters. Now, I also think that the current narratives going around the Iberian blackout will be corrected in the Philippine market. That it's not really renewables that cause the blackout. It's really a combination of factors, and that is why we have to look at our own power grid code to find out if we have a robust enough set of planning and operating parameters to be prepared for these future eventualities.
Yes, thanks a lot, Sir Bert, to also underline again this point. And indeed, I think also a specific lesson from the Iberian blackout is renewable, because of a lag in regulation, were not able to provide this voltage control, but they were technically able to do so. It's very important that actually regulation anticipate technological development and not the other way around, because in that case, renewable could have helped avoid the blackout to start with, right? So once again, thanks to all of you. I will finish with one question, which will be the same for the three of you, which is, in a few words, what is the priority from the country perspective in terms of grid development that you see? It can be regulation, planning, operation, in order to accelerate the development of renewables. So just a few words, and I will start with you, Mr. Quang. So for Vietnam, what are the priority for grid development now?
Yeah, I would say it's the most important for step for promoting grid development in Vietnam is to take advantage of any economic partners. So in this case, it's private sectors, not only putting everything into the hand of the state-owned company, because there will be like financial challenges, and also if we don't take advantage of private sectors, then a lot of burdensome to state-owned company, and we lose a lot of chance. But to do that, we need to open the legal framework to enable any business model, and also pricing mechanism that investors, the private sector, can jump into to the sectors, then everything will be dynamic and will be solved easily.
Very good. Thanks a lot, Mr. Kwong. So an appeal to private investment in the economy of Vietnam, specifically in the energy and power sector. Dr. Marojahan, same question to you. What is the key priority for grids to enable renewable energy development in Indonesia?
Yeah, simply, I think we need a regulatory framework to make VREs and ancillary services more valuable, more competitive, because mostly, our capacity expansion planning is based on least costs. So making renewables more competitive, either, I don't know, not necessarily with open market, but with something to make them more competitive, then we will have, more point forward to the renewables, more renewables. Thank you.
Thanks a lot. So maybe also re-establishing a level playing field between technologies. And final point will be for you, Sir Bert. What are the priorities for grids in the Philippines to enable high share of renewables?
Thank you very much, Dimitri. I think as far as ICSC is concerned, we always believe that there should be a policy shift to a more decentralized grid. We are an archipelago. We need more decentralization to enable more injection points in the grid. We need flexible generation. And I think coming out of this webinar, I'd like to see if we will need a revision of our grid code to anticipate, as you say, anticipate future occurrences like this so that we can prevent what we've seen in the Iberian Peninsula. Thank you very much.
Thanks a lot, Sir Bert. Thanks again to all the panelists, Mr. Kwong, Dr. Marojahan, and Sir Bert, for a very good contribution to the discussion today. And of course, thanks a lot, Arne, for your very good presentation. I'm sure we'll have follow-up questions, and also we are happy to contribute to further dissemination about this, I think, important piece of analysis. And I would like to thank everyone which was on the stage, so the panelists, also Arne, but also behind the curtain, specifically Grace and Ernst,